Hello everyone, my name is Antonella Mensi. Today I'm presenting the paper called An Alternative Exploitation of Isolation Forests for Outlier Detection, a work that I did along with master student Alessio Franzoni and professors David Tax and Manuele Bicego. The motivation behind our work is the following. One of the most successful methodologies for outlier detection is a technique based on random forest called isolation forest. As the name says, it is based on the principle of isolation, which is separating each object in the dataset from the rest independently of the class the object belongs to. Isolation forests implement these criteria by using trees that are completely random, that is, where splits are performed by choosing randomly both the feature along which to split and also the threshold value is chosen randomly in the range of that feature. So, a practical example is the following. We have some data following a distribution and we have some outliers. We can see that the inlier, which is depicted in yellow, is isolated after many splits because it is inner within its distribution, so it will take more splits to isolate it. While for the outlier, this is not true because after few splits, we are able to isolate it. In general, outliers have an higher isolation capability because it is more probable that one of the first splits will be able to isolate them because they are usually rather separated from the rest of the data. So to retrieve this isolation capability that is different for outliers than from inliers, in the testing phase, isolation forests use an anomaly score that is based on the average path length of an object. Indeed, outliers which have an higher isolation capability will end up in leaves at small depth, and thus a higher anomaly score will be associated with a smaller depth. So isolation forests thus are very interesting and they work very well, and they have been thoroughly extended, mostly concerning the training phase. That is, several alternative ways to build the trees have been proposed, but few extensions of the testing phase, that is, how can we classify the objects, how can we detect the outliers, have been proposed. We insert ourselves into this context by proposing an innovative exploitation of isolation forests. To better understand our proposal, let's take a step forward. Consider random forests for classification and regression. Other than being successfully used for the main aim, which is to classify objects, they've also been employed as data descriptors. Indeed, if we make an object traverse a tree, we are able to describe it in a meaningful way by the way it's represented in the tree. And if we have multiple objects represented in the same tree, we are able to describe the relation between these objects. Indeed, several random forest-based distance measures have been defined and are extensively used for many different applications. So, our proposal inserts ourselves into this specific context, that is, we train an isolation forest and then we extract from this forest pairwise distances between the objects. And the obtained use distance measure is then input to an outlier detector to finally detect the outliers. So, more in detail, the pipeline of the method consists of three different steps. The first is the building of the forest, the second is the extraction of the distance matrix, and the third is the usage of an outlier detector. So, more in detail, the first step is rather trivial and straightforward, due also to the explanation of the isolation forest that I did previously. So, the first is composed by several trees. We must build each tree on a random subsample of the dataset that is drawn usually without replacement. Then each tree is built in a recursive way until a stopping criteria is met, and each split is performed completely randomly, as I said before. So this is rather straightforward. But what about step 2, which is the computation of the matrix, wherein each cell contains the pairwise distance between two objects? To do this, we must first consider a tree T, and then we have to make our two objects I and j traverse the tree until a leaf is reached. In this way, we have the representation of the two objects in the tree via the path that they have traversed, that is the path from root to leaf. After having done this, we are able to compute the distance between the two objects in the tree. And after repeating these steps for all the trees, we compute the average and we obtain the element of the matrix D, ij, that contains the distance between the two objects in a forest. Obviously, if we have at step 4 a similarity instead of a distance, we will have to make a proper pre-conversion, but this is rather straightforward, let's say. The most important thing is How can we, in practice, compute step 4? In literature, there have been proposed several similarity measures. The first one goes back to more than 15 years ago. It's called the SHI similarity measure, which practically says the two objects, I and J, are similar in a tree only if they end up in the same leaf. This is rather restrictive because it means that even if they share a very long part of their paths, they will have zero similarity. So the similarity will be in a tree either 0 or 1. So since this is rather restrictive, the criteria has been generalized by, for example, zoo, which we take into consideration, for which we have two similarity measures, zoo2 and zoo3. Zoo2 practically generalizes SHI by saying that two objects in a tree are more similar if they share a longer common path. So they do not need to have the same path, which correspond to maximum similarity, but they need just to share some nodes, some traverse nodes in the path to have non-zero similarity. Obviously, a longer path means a higher degree of similarity. Zoo3 is a weighted version of Zoo2 that takes into consideration for the computation of the similarity not only the length of the common path but also other information, which is the node size. So this is basically step 2. What about step 3? Step 3 is brief, but it is very important because we have to make a wise choice in terms of the outlier detector we want to use. In general, we must choose a one-class classifier that takes as input either a density or a distance. And there are many different types because there are outlier detectors based on nearest neighbors, on density such as the local outlier factor, on clustering such as the k-means. So we have a very wise choice to make here. But after having chosen the classifier, we can finally train and test it by using the distance metrics that we computed at step 2. So while usually these classifiers by default use, for example, the Euclidean distance, now we use an isolation forest derived distance. The methodology has been tested on 10 UCI datasets that vary in terms of number of objects, number of features, and outlier percentage. Several preliminary experiments have been performed to both choose the parameterization of the isolation forest and also the outlier detector to use for the detection of outliers. Indeed, the isolation forest was chosen with default to be trained with default parameters except for the forest size. Indeed, instead of using a forest with 100 trees, the trees were set to 150. We used all the distances that I have described before, SHI, Zoo2, and Zoo3, and we performed experiments with several classifiers, but we chose the local outlier factor as our final choice with a k set to 14 after several experiments have been performed. Each experiment was repeated 20 times, and as accuracy measure, we used the AUC. So, for complete and detailed results, I refer you to the paper, but some important experimental observations are the following ones. Only one dataset, that is mask, has a performance that is independent of the distance measure, while the others tend to have some sort of preference. Only on one dataset, the most restrictive distance, which is SHI, is able to outperform the other distances, and in general, the best overall distance is Zoo2, which is the unweighted version of Zoo. So an important comparison that we did was the performance of the isolation forest alone with respect to our pipeline. That is, we train an isolation forest, we extract an instance matrix, and we inputted the distance matrix to the local outlier factor. Here we show the median across the 20 experiments. We choose the best distance for each dataset, and we can see that in general we have a better performance when using the proposed pipeline. More in detail, on 7 datasets we can see an improvement, which is in some cases statistically significant. So, in conclusion, we propose a novel exploitation of isolation forest to detect outliers. We use the forest to extract the distances, and then we use the distance metrics that we obtain as an input to an outlier detector. We work with several random forest-based distance measures that have been previously defined, and the experimental results tend to confirm the suitability of the methodology. Thank you.